Okay, here we have the integral of our density function over the circular region, the circle centered at 1, 2, with a radius of 4. So we're evaluating now the mass of the region, integrating the density over the region. And I tell you right now that there's a mistake in here someplace, and there almost needs to be. It's a circular region with this density function. I saw at the end that, yeah, this could be made sense of in terms of the average possible value of the density function, but it doesn't have a pi in it, and the area of the circle has a pi in it, so I couldn't understand how the pi could have divided out. Then I happened to see the answer, and this isn't right. So there's something wrong here, but I can't seem to find it. So hopefully going through this I'll find it. Nevertheless, I chose to do this integral in a way that illustrates a lot of important integration technique that we need in this course. So, despite the fact that I can't seem to locate the source of the error, probably will as I go through it, I'm going to still present this, okay? So here's the integral. Now, we have to integrate this with respect to y and then substitute these two limits on the integral. And I decide I'm going to let u equal y minus 2 because it makes the whole thing simpler. du is still equal to dy, so the integral can be written now this way, where instead of y minus 2 squared we've got u squared. Now I still want the same limits in the integral because I want to come back to those limits. I could convert the limits, just another chance to make an error, so I'm not going to. And I already got an error, who knows what would have happened. Okay, but I make a note that the limits are on y, so I say y equals this, y equals this. So the integral's from y equals this to y equals this, even though my integration constant here, or my variable of integration here is now u. Meaning we got to substitute back the y minus 2 for u when we get the antiderivative. Okay, well, very easy to integrate. U squared gives us u cubed over 3. And x minus 1 squared doesn't have any u dependence, so you just get u times the quantity x minus 1 squared, evaluated between here and here. And I probably should have put y equals, just to keep reminding myself so I don't go on and do something silly. That's I'm almost bound to do anyway. Okay, so now substituting substituting back the y minus 2 for u, that's easy enough, we get this, and that's evaluated from here to here. And now we plug the lower and upper limits in. Plugging the upper limit in, you see that if this goes in for y, that y minus 2 is just going to be the square root of 16 minus quantity x minus 1 squared. And that's multiplied by quantity x minus 1 squared. And that plugging in here, we're again going to have a y minus 2. It's going to give us the square root of 16 minus quantity x minus 1 squared. And that's going to be cubed and divided by 3. Then we subtract the lower limit, which gives us exactly the same thing, except we got a negative on that 16 minus quantity x minus 1 squared, and a negative on it here. Well, here it's negative. The minus gives us the same thing we've got here. And here we're cubing a negative, so we're going to have a negative here, that minus that negative is going to give us a positive, which means this term is going to match this one. So we're going to have 2 times all this stuff here. Okay? Hopefully I wasn't standing in the way of it, but just, because the minus here and the minus here, and the minus, the negative, or the, negative square root being first power and cubed, it's going to maintain the negative. The negative is going to distribute through, make these terms match these terms, so we're going to have 2 times what we have here. Okay, well there it is, and it seems very straightforward. I still don't see an error, but I've looked pretty hard and I haven't seen it, so I don't know how my mind has been rutted into some kind of an error, but it has been. Still, that illustrates the U substitution here. Then we're going to go ahead and do another U substitution because we've got all these x minus 1 squareds that we really go blind looking at. So we're going to let u equal x minus 1. Again, du is going to be, well, dx in this case. And, of course, we're going to integrate this from negative 3 to 5 because what we have here is the inner integral, and now we've got to integrate that inner integral from negative 3 to 5. So making the substitution, we have 2 times this integral. The x minus 1 squared becomes a u squared here, here, and here. Okay, so yeah, that works. I'm just checking it out. Then to integrate this, we're going to use a trig substitution. We can choose to use u equal 4 sine theta. So the du equals 4 sine theta, 4 cosine theta. Should write the d theta on that. And then it follows, if we just trace what these are, that 16 minus u squared is 16 minus the square of this. Square of this is 16 sine squared theta. So we get 16 minus 16 sine squared theta. Factor out the 16, we get 16 times 1 minus sine squared theta, which is 16 cosine squared theta. Now we've got the square root of that, and then it's times u squared. Okay, so the square root of 16 minus u squared will be the square root of 16 cosine squared theta, which is 4 cosine theta. The u squared is, of course, going to be a sine squared theta. And then, again, the 16 minus u squared is going to be, this is going to be 16 minus u squared raised to 3 halves, meaning it's a square root of 16 minus u squared raised to the 3rd power, which is going to be cosine cubed of theta times the 4, the factor 4, that you have if you take the square root of this mess. So you have 64 thirds cosine cubed theta d theta. I don't see where pi is going to come out of any of this. We're not doing arc sines and arc cosines and stuff. So doesn't mean it doesn't, and it doesn't mean it shouldn't. It means there's an error here that's causing it not to happen. There may be an error in the original function, but I don't think so, or something else. Okay, so do this integral. Well, it's pretty simple. Maybe I do see where it came from. Because where I had 4 cosines theta sine squared theta, I've got 4 cosine theta sine theta here. Okay? So, this should be sine squared theta. Okay, well, over here on the cosine cubed theta, I write that as a cosine times a sine squared. The sine squared is 1 minus I write as a cosine times a cosine squared. Cosine squared is 1 minus sine squared, so cosine cubed is cosine times 1 minus sine squared. Now this is typical second semester calculus, calculus 2. Standard technique, something you should have done a lot of times so that you recognize it when you see it now. One way or another, if you don't understand the integration technique as well as you might wish, this course should be a good cure for it, but it's going to take you a little longer. Okay, so you're going to have to practice a little more and not leave off squares on sines like you see me do. Okay, well, now I really wanted a sine here, but that's not a big deal. If it was sine squared, then I could do a substitution on this, let u equal cosine, or let u equal sine theta, so du is cosine theta d theta, and I'd have a u squared and go on from there. So I'm going to leave that to you, but this is probably a source of the error. Okay. Of course, I still don't see really don't see it. We're going to get a pi out of it, but I'm not thinking that hard. Okay, so at this stage, we use W equals sine theta, so dW is cosine theta d theta. And we have a cosine theta in each term, so we can factor out a cosine theta times d theta, and that's going to give us our dW. The rest of it, we're going to have 4W, and it should be 4W squared, so yeah, that really isn't a problem. Kind of gives a W cubed over 3. I'm not going to correct it now, but right there's where it is. Should be a W squared. And then 64 times 1 minus W squared. W is a sine theta. There it is. And now it's a very simple integral. We integrate it. And then we back substitute. We substitute for the sine. The W equals the sine of theta. Make sure I was doing that right. Okay? And then what's sine of theta? Well, sine of theta is u over 4. So if I substitute u over 4 for every sine, I'm going to end up, well, I haven't actually done it. I've also taken the fact that u equals x minus 1, so sine theta would be u over 4, but that would be x minus 1 over 4. So now if every sine theta is replaced by x minus 1 over 4, I get this. That looks good. I get this. That looks good. And I get this. And 4 cubed, yeah. I don't know. I don't see an error. Anyhow, that's evaluated between between -3 and 5. And you come over here and I do that in my head, so it might or might not be right, but I'm pretty sure of it. So I still don't see any problem with this integral, except that this should have been there's actually an error here. I get W squared over 2, and 2 goes into 4 2 times, and I put the 2 down here. Okay, that should have been a 2W squared. This is really 4W squared. This should really be 4/3 W cubed here, which is going to give you something quite different here. It's going to be pretty small, so I don't see what's going to greatly affect that. But it's cubed, so yeah, you can evaluate this. I'm afraid you're still not going to get what should be the correct answer if Webb's sign is correct, and it usually is. So there's still something going on in here, so you want to be careful about it. But that's a demonstration, at least, of a good bit of integration technique.